This is actually not my major area of research, but it's a core area of research. So I wanted to start with this diagram. And by the way, the arrows should connect. This is an older version of the presentation that somehow the corrected graph didn't make it through. But this is an old diagram that was published in 2003 by Susan Cutter, really looking risk through mitigation. I made some changes, but basically the idea is that the top part of the graph is focused on physical risk and relation to infrastructure, and the bottom part of the graph is really related to the social aspects of risk and how important they all are in terms of determining vulnerability of places. So a quote for AI. So AI is very different from machine learning, right? We have been doing machine learning for over 30 years. And what AI really brings that is different is the power of technology, of using almost analog versions of computers to actually do very deep learning and go through large data sets and identify patterns and so on. So it's really, we go from the 3 or the 4 dimensions of how we usually think of place, X, Y, and Z, and time, right, T. And now we're thinking about a world where we have N dimensions, where the other axes are really associated with different processes, spatial organization, social decisions, etc. I'm going to focus here on 2 aspects of the use of AI. One, AI for planning, which I really think is the most productive at present, and AI for mitigation, which I think is the most exciting because is the one where the challenges lie, and that's in terms of prediction. So I'm going to focus on flash flood prediction. So first, in terms of AI for planning, what are we looking for? We're looking forward to understanding the threat, and that is essential to actually characterize risk, identify vulnerabilities, whatever they might be in the landscape, and then determine consequences. And for this, we have huge data sets, right? All kinds of data sets available everywhere. And so we're going to connect, or we can connect, geo-AI, which is basically GIS on steroids, with good quality data, and then connect that with our physical models and algorithms. And what's essential to really keep the human element is interpretation, right? That's very important. AI cannot do interpretation for us. We must do the interpretation. And that ultimately looking to the contextualization of risk. And of course, I'm going to be presenting from a US perspective, where we're going to look at these very large types of extreme events that we have happening there. So I'd like to start by looking at this right-hand side here. And what you see are 2 maps of billion-dollar disasters in the US in 2 different years. And the point here is not to focus on individual disasters, but to look at the spatial organization of these disasters, right? And what you see is that year in and year out, these types of disasters that are all kinds are actually happening in the same part of our landscape. So if you look now at the map of the US, you'll see, of course, the Rockies on the left, and on the right, you see these little mountains, the Appalachian Mountains, that don't look very significant. Actually, the highest elevation is only 2,100 meters or so, and yet they're actually controlling a lot of what happens in terms of weather and in terms of orographic enhancement of precipitation. This map shows a distribution of hydropower producing plants, dams actually in the US. And the reason why I'm showing this is because you'll see that they are aligned with mountainous regions. And so basically they're all placed along the steep slopes and within 2,000 or 3,000 meters of elevation, because you need the height to actually produce the power. Now, how do we design dams? We design dams for the PMP, which is the probable maximum precipitation. And what's the probable maximum precipitation? We don't really know, right? What we have are observations of maximum amounts that were measured at specific locations. As you can see, in the US, in states like Texas, we have measured in the past very close to about 1 meter of rainfall in one day. That's an extreme, right? And so when we're thinking of designing for this dam here, we're thinking about what would that look like at that location. So this is a map of our estimates of the 1,000-year flood, which is sort of an equivalent of this probable maximum flood. And when you look at that, you'll see that we're predicting about 1 meter of rainfall everywhere along the coast of the Gulf and of the Atlantic coast. And this is where we have landfall of major hurricanes, right? As the hurricanes move into becoming a tropical storm and move over land, what happens is that as they move in and they basically interact with the topography, then we have orographic enhancement in those locations, and we basically can produce the same amount of rainfall that you have at landfall. Meaning, anywhere in these little mountains here, we can, as we did last year with Helene, observe at several locations about 31 inches of precipitation in 24 hours, which is about 800 something millimeters of rain in one day. Now think that the previous week we had Erin that had also produced a lot of rainfall. So this is the kind of extreme we're talking about here, and how important it is to have this regional perspective of this. And if you look at the yellows, you look for them along the mountains and along the coasts. The other aspect of this, though, if we look at the smaller floods, not the 1 meter in a day, is a study we did several years ago looking at flood and flood variability. Is that a sign of climate change in the flood variability in the southeast US? And what we found was that you see these outliers, all those little red dots or circles are actually outliers of our distribution, meaning extremes that are out of the normal distribution, right? And you'll see that, for example, Houston has a big problem with floods. It's not actually a natural process. It's because of the lack of conveyance in the infrastructure system of Houston. But when you look at this, what you'll find is that actually these outliers are aligned exactly with interstate highways, right, and huge areas of urban development. So you can see at major continental scale almost effects, right, of urbanization in the risk scene that we would like to analyze. This example I'm showing because the importance of looking at landscape, not just as a topography map or elevation or even slope, but actually looking at landform. So that's a picture of the Pecos River Bridge before the big flood of 1954 that basically wiped that bridge completely. And this is the current bridge that is actually sitting in the same place. So the difference is that, and this bridge will stay there, I believe, for 1,000 years or so. We'll see. I will not be here to be proven wrong. But what you'll see there is that that bridge is basically on the flood, on the valley, right? It's in the floodplain, whereas this bridge was built on the top of the bluffs. So when we look at the landscape and we have bluffs like this, the message is the reason why they're there is because many huge floods have happened in the past. And so the likelihood that that's going to happen again is right there, right? Whether it's very high or very low, from a risk perspective, as Anne-Marie was saying this morning, a 100-year flood could happen tomorrow, right? So the extreme flood could happen tomorrow, as happened in 1954. This is a copy, this is a photo of the bluffs in the Guadalupe River, where the big flash floods happened this summer. And so if you have a river that looks like that, right, this is why we have to really change how we communicate risk. It's important that communities look at their own landscapes and understand the risk they are in. Now, what AI cannot do for us, I said before, is interpret. It cannot think for us, even though there's all kinds of articles about that, right? We're all going to be retired soon because AI will take over. AI will not take over. So this is results of a study we did in North Carolina looking at how can we explain the origination of shallow landslides in the southern Appalachians. This is an area with lots of earthquake activity, so everything is kind of shaken up. And then when you have a very heavy rainfall event, we have lots of shallow landslides, end up in lakes and basically impacting water, potable water, like in Asheville, they were for 2 months after Helene without fresh water. And of course, it can destroy roads and all kinds of things. And so what we did here, this is a physical model. We had all the data collected by the North Carolina Geological Survey of time and place where these landslides happen. And we were able to show with a very detailed hydrology model that these landslides happen when we have the maximum interflow in the hill slope. And we can identify exactly the time when that happens. So if we can predict precipitation way ahead of time, we can actually also predict, right, where these landslides are likely to happen and get people out of the way. Now, what AI can do, interflow is flow in the soil layers, in the upper soil layers, exactly. It's not flow that comes from the groundwater system, but it's flow in the upper soil layers. Thank you for asking. So now let's talk about this idea of how do we predict precipitation? Can we get it right so we could get it, if we knew what the scene is in terms of risk context for our region, for our landscape. How do we do that? We're interested in long lead time forecasts because that's what emergency managers and city councils and so on need in order to make decisions, right? And so before I actually go into showing results of our model, I wanted to show this is state-of-the-art nowcasting model looking at prediction of heavy precipitation. And I want to focus here on this slide. This is a very low standard. If you think about that, it's precipitation intensity hourly of 8 millimeters per hour, right? Which is a convective storm for those of you who are familiar with the terminology. Now, using this system, which is really, it makes a lot of sense using radar information and so on, what you can see is that within maybe 10 minutes, actually, the predictability of this amount of precipitation is below this level for the critical success index, which means that you could do better if you were just saying, oh, it was raining, now it's going to be raining for the next 10 minutes, right? That means there's no skill, basically, in this kind of AI system. This was published in Nature. I don't want to be negative about my colleagues' work, but it's just to tell you how hard it is to get precipitation right? And how we need to do very hard work to really get at estimates that make sense. And this is also why, because our observing systems, those radar fields, are severely biased, because they have to be operated in ways that we minimize things like ground clutter effects and artifacts and so on. So the data themselves are heavily biased. And it turns out that we end up missing the heavy rainfall, especially in mountains where it's hidden. So now our model, so what we do, it's very simple here. It's actually a very simple approach. We take national weather prediction output of precipitation from the National Weather Service. We process it through an AI-based model that's actually very simple, using random forests, really the simplest of models, and we train that against a data set of optimal observations that we have built over the years. And we calculate a correction for the weather forecasts. After that, we take that correction and we downscale precipitation and we run our hydrology model. And so we produce flash flood forecasts over 30-something basins in the Great Smokies National Park. So we're working with the National Park Service in this project. And anywhere in over 1,000 kilometers, actually, of stream network, so we're talking about very, very small streams, anywhere in the mountains, we can produce a flood forecast. How good are our forecasts? I actually would like you to focus on this one. And it was selected not because it's our best, but because it's our typical, right? So this is a flood that's not a hurricane-related flood or anything. It's just a basic convective storm flood. And these are the observations. And these are different forecasts we made with a lead time of 30 hours. A flash flood will take place between 0 and 6 hours. So usually in most small basins, it will be a couple of hours and you have the flood wave basically going through. So the point here is that this is an excellent forecast. Not from the point of view of myself as a scientist and trying to get the peak right and the timing right and all of that right, but from the point of view of an emergency manager. Why? Because I know enough ahead of time that I'm going to have a flood that's an order of magnitude above what the average annual flood is at this location. I know that I know how fast I know it's going to be a flash flood because it's very fast rising, right? And I know that with enough time ahead that I can actually make some decisions, evacuate people, get people out of the way, etc., right? So that's the kind of standard we're using here, not the standard of using those curves of the critical success index that I was showing before. So we have this model, we have ran it for lots of flood events, it's doing really well, it's very reliable, and it does the best at this kind of time scale because of different reasons. The forecasts are really bad at long time scales, and they are sort of, we're plagued by uncertainty at very small scales. This is what the API looks like, what FloodView looks like. So everywhere in the system, you can actually identify camping sites in the national park, where the structures are, where roads are, etc. And you have a forecast with a lead time. You have the precipitation. You have also the stream flow. And you have some information about the level of severity. Now, this is an example of another forecast for Hurricane Helene. The flood at this location was 35 times the annual flood in this particular basin that I'm showing here. We were able to predict 20 times the annual flood, right, with 18-hour lead times. That's pretty good. That's actually very robust. If we can do this all the time for extreme events, then we are in really good shape. And that's the goal of this API in support of the National Park Service, of the rangers, and also, they're very concerned that people will go camp somewhere and then they will be caught, as it has happened in Arizona and so on, by one of these events. And this is just my conclusion. And so thinking that, it's not perfect AI, we're still very important, I believe. It's very powerful, though, because it gives us so much analytical power, right? And that's what we can harness and really use our creativity to improve our forecasts. Thank you.